up next, we have ICN2. Now, if I'm right, ICN2 is Stefan. Is that you, Stefan Roche?
Thank you. You hear me?
I do. I ask, are you okay getting your slides?
Yeah, sure. Thanks. Okay, so the main goal of our module is to introduce the student with the fundamental concept and computational tools also to study topological properties of quantum materials. Okay, so for the moment we are planning the module to be divided into two main sections. One will be to have a series of short, like 10-minute long lectures using digital board for introducing the theoretical minimum about the concept that we need: symmetry, topology, entanglement in quantum matter. And then the second part will use Python libraries to compute numerically some of those properties like Berry's curvature, topological invariance, and so on and so forth. And the used algorithm will be developed inside our in-house LS-Quant software. So we will also include some tutorials or to use this algorithm so that then the student can solve some typical problems and can master those modules. Just want to, I mean, this is a kind of a list of concepts that we would like to introduce in these lectures, and then having the student to practice some of these concepts by the simulation tools that we will provide. So I will not go into the full list that are all that you need to know if you are interested in quantum materials and their use for quantum technology or even quantum information. Then we already have an online platform where we are starting to connect with a large community concerning the release and the dissemination of this LS-Quant linear scaling quantum transport methodology. So linear scaling in the sense that it allows to, the cost of the computation is just scaling with the number of orbitals of the Hamiltonian. So we have achieved quite some world record of the complexity of the system that we can investigate with those objects. So the idea here is to, for the moment, to have a direct entry point to for the students to the lectures and all the materials through this interface, and then to work on that. I would just like to in a two slide to give a flavor about what we mean by this simulation tool. This is, for instance, an implementation we made several years ago to look at the quantum Hall effect in very complex two-dimensional materials with some disorder, and we achieved the simulation of very large disorder system with a magnetic field that could be as small as 1 millitesla, which was really something unprecedented with existing tool. And also these tools are easily parallelized and can be transferred to high performance computing platforms and so on and so forth. So the way the tools, for instance, are working is they need to have as an input the structure of the materials, and then to define an Hamiltonians which connect the orbitals with the energy hopping and so on and so forth. And then the code is written in Python and use the Google Cloud also platform in order to run our codes, and so the student will just have to connect with the platform and make the calculation. For all, we are also thinking to have an internal computer workstation dedicated to the project where they could also directly launch some simulation by connecting to ICN2. Okay, so that's very short, but I hope that it gives you some idea about what we are planning to do. A question?
Any questions for Stefan? Jacob, you would like to ask?
Yes, just a question and maybe a comment to everyone that what do you see as the requirements in order to go into this? And then maybe all of us could really sort of quantify that so that it's very clear for all of the course providers.
Oh, I understand that the basic knowledge of quantum mechanics is enough. I mean, the introduction to the Berry's phase is something that can be done maybe in a couple of 10 minutes long lectures. So usually a grade in physics is appropriate. Maybe people coming from an engineering studies and with a weak knowledge of quantum mechanics might be in difficulty. But I think that we will try to really get the or can I say the theoretical minimum provided to the students, so that then they can understand, I mean, use the methodology in order to practice on some Hamiltonian with some guidelines. So, but I think it's really within the reach of students who have a degree in physics or grade or graduate in physics.
And thank you very much. And so we can work together to try to find the most compact but also applicable way of formalizing what the requirements should be in order to enter these kinds of things, right? So that it's very readable. Thanks.
Okay.